Hi there, welcome back. This is lesson 2 of our nuclear chemistry unit. Like as promised yesterday, we are going to spend today practicing nuclear decay modes. So there is a sheet on the website that is titled Nuclear Decay Practice. So if you wanted to take the time to work on that and then come back here to check your answers, you can do that, or for explanations, you can do that. If you want to watch it and kind of work side by side, that is totally okay to you, whatever makes you happy and whatever works best for you. So, before we move on, just a reminder that Castle Learning number 26, Nuclear Decay, is due tonight by 11:59. Just make sure that you are following the announcements and any other updates your teacher may give you. So, writing nuclear equations, and I'm not going to read this entire paragraph for you. You're all capable of reading. But when we're talking about how an element, how its nucleus changes to form different elements, and that's what nuclear chemistry is. And so when that unstable nucleus changes, and that's, I will highlight this, where transmutation comes into play. That's when the element changes into something else. It mutates or becomes a different element. And in that process, it releases a nuclear decay particle, and that's what table O tells you. So table N and table O are the go-to unit reference table sections for this unit. Table N, we're going to work with this more towards the end of the week as well. But it tells you, the half-life of something, which is later in the week's topic, and what kind of decay mode it goes through. And then table O tells you, what that specific particle does. So like the mass and the charge of that particle. Okay, so we're going to need to be bouncing back and forth between this. So in order to find the decay mode, table N does that for you. All these 10 elements are found on table N. And then when we write the equation, we can use table O to kind of get a better idea of what that particle looks like. So, calcium 37, according to table N, the decay mode is beta positive, and this is a positron. So remember, a positron is a positive electron, really. So it has 0 mass and a positive 1 charge, and it's symbolized like that. I'm going to say beta positive just because it's easier than saying positron over and over and over again. If we're talking about beta particles, also, and when I get to there, you'll see what I mean better. That'll be beta negative. Anyway, back to this. So that top number is the atomic mass, and we're dealing with calcium. And so you have to look at the reference table, at the periodic table, to see that this is 20. The atomic number, remember this number, the atomic number is the number of protons. It is specific to every single element. So calcium is the only element that has the atomic number 20. And this is going to break down into, well, we know it's releasing a positron. And so we have to figure out what the other object is. And so to find out the mass of that object, something plus 0 has to be 37. So that means 37 goes in that box. And for down here, something plus positive 1 has to give us 20. And that is 19. And then this 19 will tell us what element we're working with, and that is K, potassium. Number 2, iron 53, is a beta positive, and again looks like this. And if we're going to write that in an equation, we have 53 Fe. You do have to go back and find 26 on the periodic table. So there is a lot of reference table flipping back and forth, but you can handle it. And we know it is releasing a beta particle. So all these all the questions that we're seeing are unstable radioisotopes. So all these decay processes happen spontaneously. So that's how we know the particle is a product. And again, something plus 0 has to give us 53. So we know that's 53. And then something plus positive 1 has to give us 26. So we know that has to be 25. And element number 25 is Mn, manganese. And that's it. The more you practice this, the more it will kind of make sense. Neon 19, again, is another beta positive particle, a positron. And it is written like this. And so you have 19 neon. And neon is element number 10. It's breaking down into 0 plus 1 like that. And something else. So the mass is still 19 of this mystery element. And then its atomic number is 9. Because 9 plus positive 1 gives you 10. Again, everything needs to be balanced. And then fluorine, F, is element number 9. Moving forward, potassium 42 is beta minus, and it's notated as this. So, and this is kind of the trickiest one because the negative is involved, but do not worry, I will help you. You have 42 K, and you have to use the reference table to find out that K, potassium, is number 19. And we know that's decaying in with this particle. So the top part's super simple. It's 42, because 42 plus 0 gives you 42. Now the bottom number is where it gets a little bit tricky. So 19, if you write it like this, equals negative 1 plus something. Okay? So if you can do this in your head, that's great. If you need that extra kind of step, this is why I'm walking through it. So how do we get this x by itself? Add 1 to both sides until you get it to be 20. So 20 plus negative 1 is 19. So that balances out. And then element number 20 is calcium Ca. Moving on, iodine 131 is a beta minus decay. And again, it's notated as, this is a minus 1, like this. And if we're writing our equation, again, that much is given to you. 53 comes straight off of the periodic table. Iodine is the only element with the atomic number 53. Breaks down into this. So we know the mass has to stay the same, so 131. And again, if we follow the same method as we did before, 53 equals negative 1 plus something. Add 1 to both sides. This has to be 54. And then element 54, according to the periodic table, is Xe. So again, once you get through these questions over and over again, it becomes a lot more simpler. At least I think so. If you're still a little bit confused, it's okay. Practice will help you. Number 6, strontium 90, according to table N, is beta minus. Again, it looks like this. And so if we write our equation, we have strontium, the mass is 90. So again, that's the mass. 38 comes straight from the periodic table. And we know it is going to be releasing a beta particle. The mass is still 90. Following this format, 38 equals negative 1 plus something. Add 1, you get 39. And then element 39 is yttrium, which is symbolized by Y. Okay, let me change colors. I'm getting tired of orange. Let's do black. Okay, number 7, radon 222. According to table N, is alpha decay. And again, that is denoted like that. And you can also write it as a helium atom. I like using the alpha particle symbol because it looks fancy and more complicated, but it doesn't matter at all. So again, we have 222 Ra, and then the atomic number for Ra is 86 according to the periodic table. And we know it's going through alpha decay, so it's releasing that. And we have to get something else. So if we're going to focus on the top, you have 222 equals 4 plus something. And to figure that out, you minus 4 from both sides, so you get 218, like that. And then for the bottom, you have 8 equals 2 plus something. 86 rather, sorry. Minus 2, so minus 2 from both sides, and you get 84. Until you get 84 on the bottom, 218 on the top, and element 84 is polonium. Okay. Francium 220 is alpha decay. And again, this is 4-2 that. So we can start off with this. And again, francium is number 87. We know it's going to release an alpha particle. And so if we're looking at the top, 220 equals 4 plus something, minus 4 minus 4, you get 216. And then for the bottom, 87 equals 2 plus something, minus 2 from both sides, it's 85. And then element 85 is At. Moving forward, we have thorium and a wonderful picture of Thor, because why not? Thorium 232 goes through alpha decay. It looks like this. So again, they all start off the same. Thorium is element number 90. We know it's going to release this. And so, if again we're focusing on the top, 232 equals 4 plus something. We minus 4 to both sides. We get 228 on top. And then bottom, we get 90 equals 2 plus something. Minus 2 minus 2. We get 88. Element 88 is Ra. Okay. Last in this section is gold 198. This is beta decay, so beta minus. It's written as this. And so again, starting off the same way. Gold is element number 79. We know it's going to release this particle. So 198 equals 0 plus something. So we know that's 198. And again, for the bottom, 79 equals negative 1 plus something. Add 1 to both sides, you get 80. And then element 80 is Hg, mercury. So, now that we've kind of established how to do this, let's take it and kind of apply it to something called the uranium challenge. So, uranium starts off a chain reaction. So, kind of like if you set up dominoes, once you knock one over, that knocks over another one and another one and another one. So once uranium starts to decay, it produces one thing, and that produces another thing, and another thing, and another thing, and another thing, and it keeps just going and going and going. So in order for uranium to break down into a stable nucleus, it needs to go through 14 different decay processes. So that's what we're going to work on. We're going to work through all 14 of those decay processes. So I started it off for you, and we are starting with uranium-238. And I'm telling you it's an alpha decay, so we know. And here I wrote it as a helium atom, same thing. And so you get thorium-234. And so now this product is now the starting material for the second equation. So if you could potentially just write this down in one very, 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 very long equation. We're just going to break it down by step. So this is the beta decay. That's where this comes into play. And now this product is our starting material for the next one, and so on. Okay? So the first 4 steps I did walk you through. Let's work through the last 10. Okay? So here, this is going to be our starting material for step number 5. 230-90 thorium. So we know, I'm telling you, it's going to go through alpha decay. So it's going to release this. And now, to keep everything balanced, this number up here has to be 226, because 4 plus 226 is 230. And then 90 minus 2 is 88. Element 88 is Ra. Now, Ra becomes our starting material for the next step. And then we know it's an alpha decay. So again, it's going like that. So now our new top number is 222. Our new bottom number is 86. Element 86 is radon, Rn. And just kind of keeps continuing this process. So now, Rn222 is what we're starting with over here. And again, it's another alpha decay. So we're left with 218, 84 polonium. Now, gotta keep going. This is our starting material for the next one. So we're starting with, so I'm just going to rewrite step number 7 right here so we can kind of follow along. So this is something we did on the previous slide. Okay. So now, again, the step 7 is where we left off here. I'm just repeating that last step so we have it. So now, 21884 polonium is our next starting material. It's going through alpha decay. And so we're left with 214 and 82. And that is lead. Now this becomes the starting material for step number 9. So we get this. Now lead 214 goes through beta decay. So it releases a beta particle. And so our other product is 214, 83 Bi. And now this becomes step number 10. Hopefully you're starting to kind of see how this is working. Bismuth 214 goes through beta decay, like we said right there. And then the top number is still 214, the bottom number is 84, and we're at polonium. So yes, you'll notice we had polonium at the first step on this slide, but now the mass is different. Okay. Almost done. I'm just going to rewrite step number 10 so we have it to refer back to. This is where we ended up on the last slide. As I was putting this together, I thought of a really fun way to do this if we were in class, kind of have this as a race, but unfortunately we are not in that scenario. It is okay. Okay, this is 84. Now, this becomes our starting material for step 11, 21484 polonium. And this is going through alpha decay. And so we get 210 on top over here, and 82 down there, and that is lead. And so now this becomes starting material for number 12, 210, 82 Pb. This is going through a beta minus decay, like that. 210 on top, 83 on the bottom, which is bismuth. Now this becomes the starting material for number step 13. Get 210, 83 bismuth. This is going through beta decay. And so we have this. Again, we're back to polonium, but we have, again, another different mass. Our last step, this will become the starting material for number 14. Let's just backtrack a second. Let me rewrite step 13 so we have it. 3. Okay. Our last step of this. This is our final reactant. And it's going through alpha decay. And so we are left with 206 on top, 82 on the bottom, and that is lead. And that is our final stable nucleus from uranium. So we have to go through all of those steps to break down and become kind of stable. So you might be asking yourself, well, how fast is that? And when we talk about half-lives later on this week, you'll see that some of these things happen pretty quickly, and some of these things happen literally billions and billions of lifetimes. So, on that note, that is it for this lesson. I hope this helped. Tomorrow we're going to start going over what nuclear fission and fusion is, and then we have just half-lives left. So this is a very, very short unit, and once you kind of figure this out, the content itself isn't super challenging. So on that note, have a wonderful day.